we will be using the second derivative test to solve for local maxes and local mins, or saddle points. So what is a saddle point? Well, a saddle point is a point that is still an extrema point, but it's neither a local max or a min. It's a point where both the x and y partials are equal to 0, but it's neither a local max or min. And you don't need to know what this looks like, you just need to know how to do the math, so that's what I'm going to show you guys today. You can honestly plug it into Desmos, like some of these graphs into Desmos, and then, or look at a picture of an example of saddle point. Like I searched up saddle point on Google back then, and it showed like a perfect example, so that's a good idea. So our first function will be x to the power of 3 minus 12xy plus 8 to the power of y. 8 times y to the power of 3 is equal to our function xy. So let me actually write down the second derivative test first. F of double x. So this is the second order x partial of x null y null f y y x null y null minus f of xy x null y null squared. And this is equal to d or something like that. D is something. So for this, we need to first find the extrema points in order to even plug these x null and y null values in. So let's go ahead and find the extrema points. Let's go ahead and get the x partial and the y partial. The x partial for this equation is 3x squared minus 12y, and the y partial is 24y squared minus 12x. We need to set these equal to 0. What we can do, we can factor out 3 at the top equation just to make things look easier, equal to 0. And we can factor out a 12 for the y partial. 2y squared minus x is equal to 0. We can get rid of the 3 and the 12 because they don't really matter whenever you're trying to get to 0, so let's just erase them. And we're left with kind of a systems of equations here. So what can we do with this? Well, we need to find some x and y values that make 0 hold true. How can you do that? Well, you can use substitution, you can isolate something, and this right here, it looks pretty easy to substitute. We can actually turn this equation into 2y squared is equal to x. We could substitute 2y squared into this top equation here. So when you do that, you're substituting 2y squared into x minus 2y is equal to 0. Then once you do that, you get the equation 4y to the power 4 minus 4y equals 0. You can factor out a 4, and then the 4 doesn't matter when you're getting to 0. And then you can get this equation here. This is y to the power 4 is equal to y. What values of y hold true here for here? Well, y is equal to 0 or 1 here. It's the only cases in quartic functions where y value would be equal to itself. 0 and 1. So then once you get this y value, 0 and 1, you need to look in your original functions, just like how you're solving for a system of equations. You need to look at the original function you plug the value in. So you need to look at x squared minus 4y is equal to 0. Right? And you need to plug in for the value of y that you solved for. So if you plug in 0 here, where can I do this where it's like not confusing? I think I'll do it here. So if you plug in 0 here, you get the equation x squared minus 0 is equal to 0. So what value of x makes sense here? Well, x is equal to 0 in order for x squared to equal 0. And then we can also do x squared minus 4 because we have 1 for the value of y. And keep in mind that our point here used the value of 0 for y and the value of 0 for x, so our point is 0, 0. And if you do x squared minus 4 is equal to 0, x right here can equal to negative 2 or 2. So our points for this, we use the value of 1 for our y value here. So our points for the extreme point would be negative 2, 1, and 2, 1. Now here's the thing. This isn't it. This isn't everything, because we need to plug in these values into our second equation. We need to meet the conditions of both equations for the y partial to equal 0. Currently, these points work for our x partial equation, but does not work for our y partial equation. So let's do that over here. Let's rewrite the function that we have to use. And let's plug in the values of our points to see if they hold true. So we'll use red again. So 0, 0, does this hold true? Well, yes, it does. This is like 2 times 0 squared minus x equals 0. So 0, 0 works. We'll put a check mark next to that. How about for negative 2 and 1? Let's try negative 2 for the x value and 1 for the y value. So we try negative 2 here. We try 2 times 1 squared. Negative 2, this is plus 2 here. Equals 0. This does not hold true. So this is wrong. This point is not an extrema point because it does not meet the conditions of both of these system of equations. Okay, let's use another color. Let's use like purple. Yeah. How about for 2 and negative 1? Well, we use 2 for the value of x right here. So we use 2 here and 1 here. This is what we get. 1 squared plus, actually it's minus 2 because x is subtracted equals 0. Does this make sense? This is 2 minus 2, which is equal to 0. So yes, this point works. So our two extrema points are 0, 0, and 2, 1. And let's erase everything else for our work for now. Now we're going to be using the second derivative test to determine if these extrema points are local maxes, mins, or saddle points. So let's leave these points at the top. We can erase the check marks because we know they're already the extrema points. And using these extrema points, what do we do? Well, we first have to find the x, double x partial, and the double y partial, the xy partial. I don't know why I erased them. I'm not going to do that next time, but let's go find them again. I'll just rewrite them. And this one is 24y squared minus 12x. So we need to find the double. Actually, these could be moved up here. I feel like this would make more sense. So we have more space here. Double x partials. So we need to find the double x partial and the double y partial. And the double x partial would be 6x. The double y partial would just be 48y. Okay. Now we need to find the xy partial for our second derivative test here. So the xy partial would be x. The x partial? Yeah. Derived with respect to y. And with respect to y, it is negative 12. So now that we have all our partials here, which is the important part, we need to plug in the values of our points. So let's go ahead and do that. X, we plug in, let's use this one first. Let's use the 0, 0 extrema point first. Put a check mark next to it to show that we have used this one. If we plug in 0, 0 for our x double partial values and our double partial y values and our double partial xy derivatives, we get, well, this doesn't have any variables in it, so xy stays the same, so it's still negative 12. But these have variables in it, and if you plug in 0 for any of them, they just equal 0. So if we put the values of 0, 0, and negative 12 here, what do we get? We get 0 times 0 minus negative 12 squared, which was equal to, well, this is equal to negative 144, but all that matters is if this is negative or positive. Once we found the value for this, I'm going to write out the conditions for our second derivative test. So let's write out the conditions. So our answer for the second derivative test, or whatever value we got, is just d. Right? So our conditions would be if d of xy is greater, no, let's write less than 0, then point P is saddle. And I'm just going to omit the if. If dxy is greater than 0 and f of xx is greater than 0, then P is a min. And if dxy is greater than 0 and fx is less than 0, then P is a max. So what are these conditions? Well, if the answer that we got from the second derivative test, which we got negative 144, is less than 0, then the point P is a saddle point. So this 0, 0 point is a saddle point. How about if d is greater than 0? Well, there's two cases if d is greater than 0. But if d is greater than 0 and the double x partial is also greater than 0, then the point is a local min. And if d is greater than 0 and the double x partial is less than 0, so if the double x partial is negative, P is a max. In these conditions, you likely have to memorize. So just keep in mind that if you get a negative value for your extreme point in the second derivative test, then it's a saddle point. If it's positive, it's either max or min using the x partials. Erase too much. Set up for the next extrema point. So the next extrema point would be 2 and 1. I'll just fill in 2, 1 here. If we plug in 2 and 1 for our x and y partials, not partials, x and y, double xy partials, you get 2 for this. So this gets 12, and then you get 48 for this because the value of y is 1. This, no matter what, stays negative 12, so we just keep this still. So what do you do? Well, let's go ahead and plug in our values for the second derivative test. What do you get? Well, you get 12 times 48 minus negative 12 squared. Well, at a glance, you can already tell this is positive. So I'll just write down positive. There's no way 12 times 48 is going to be less than 144. So this value we got for d is positive. So if d is positive, remember the conditions. If d is positive, then it's either a local max or min at 0.21. Well, let's go look at the double x partial next. So remember, in the conditions, if the double x partial is negative, we have a local max. But if the double x partial is positive, then we have a local min. So what is our double x partial here? It's positive. So therefore, dxy is positive, let's change the color for that. dxy is positive, and f of x is positive. So we have a, let's use blue. So we have a local min at 0.21. Now I know the steps for that's long, but the longest part is honestly just finding the extrema points. That's the hardest part. Once you have the extrema points, you just have to plug it into this equation here. And this equation literally just tells you everything that you already need. You don't have to memorize any of these steps. You can look at this equation. It tells you everything you need. Only thing you have to memorize are the conditions. But besides that, finding the extrema points is still the most tedious part because it's all algebra. Let's do one more problem because I know that one was pretty long. Let's do the problem ln of 1 plus x squared plus y squared is equal to our function. So this is our surface in a three-dimensional space. What do we do first? We have to find the extrema points. How do you do that? We need the x and y partials. First get the x partial for this. So the x partial for this would be 2x over 1 plus x squared plus y squared. Notice how I chain ruled the x squared and then multiplied it by the derivative of any natural logarithmic function. And our y partial is, again, quite kind of similar to the previous one. But again, I use chain rule on the y squared in the denominator. So these are two x and y partials. What do we do next? Well, we need to set these equal to 0. That's quite tedious, isn't it? Well, no, it's not. I thought it was tedious just now because I don't solve these problems beforehand. But what actually matters is the numerator. The only time when a fraction can equal 0 is when the numerator is 0. Besides that, if the denominator is equal to 0, well, then you have a problem. But in this case, the denominator can never equal 0, knowing the properties of a squared function. X squared plus y squared plus 1 can never equal 0. And the reason why is because even if the lowest number that x squared plus y squared can get to is equal to 0, correct? Even if they get to this number, you still have a plus 1 here. So the denominator here can never equal 0. Because of the properties of a squared function. Squared functions could only be positive or 0 at lowest. And at the lowest, this equals 0, but we have a plus 1, so the denominator can never equal 0. We don't have to worry about that. We can actually change these functions just to just equal 2x is equal to 0 and 2y is equal to 0. Once you have 2x equals 0, 2y equals 0, what satisfies these conditions? Well, x equals 0 satisfies this condition, and y equals 0 satisfies this condition. And in this top function, since there is no, in this function right here, up top, since there's no y value, y is free, so it can reign over anything, any value. And using this, it doesn't matter what our y value would be for the bottom. So our critical point that we found is 0, 0. That's the only critical point that we find, actually. Yeah, that makes sense. Okay, so our critical point 0, 0. Does that work? Well, that obviously does, because if we plug in 0 for the x value in our x partial and the y value as 0, we get 2, 0. We get 1 plus 0 squared plus 0 squared, which is just equal to 0 over 1. And this does equal to 0. That's the same thing for the y partial. So now that we have the critical point of 0, 0, we check this off because it works. What do we do? Well, we have to use a second derivative test to figure out if this is a local max, min, or a saddle point. Let's go ahead and do that. Let's plug, but first, we don't plug in anything. We need to find the double x partial and the double y partial and the xy partial. So the double x partial would be something very annoying to find out. Okay. Let's make some space for this. Let's use the quotient rule. quotient rule would be 1 plus x squared plus y squared. Oh, Jesus Christ. Minus high d low 1 plus 2x plus y squared over 1 plus x squared plus y squared squared. This is our double x partial. But it's not that annoying because since our points are 0, 0, a lot of these are just easy, really, really easy to calculate. So our double y partial would be, let's use the quotient rule again, low d high, so derivative of the numerator, minus high derivative of the denominator, d low, over low, low. We'll just low multiply by each other, so it's just low squared. And this time we derive twice with respect to y, and this one we derive twice with respect to x. That's the little differences that you see in each of these quotient rule problems. And we need more space. Great. Let's remove this. What did I do? And let's go ahead and find the xy partial as well. So the xy partial is a little easier to do. So let's look at the x partial. The x partial is 2x over 1 plus x squared plus y squared. We derive this with respect to y, and the only place that has r value is this down here. So all we have to do, our value of y down here. So all we have to do is treat x as a constant, and this is simply a power rule problem. So technically this is 2x, this is not our double xy partial. Technically this f of x is equal to 2x 1 plus x squared plus y squared to the power of negative 1. If we use power rule here, we have to put negative 1 down. Then we have to subtract 1 from the exponent. But we're not done. We have to use chain rule on this. So we have to use chain rule on our y squared. Once we use chain rule on that, we get 4xy. 1 plus x squared plus y squared to the power of negative 2. If we just make this look like a fraction, we get 4xy over 1 plus x squared plus y squared squared. So this is our xy function here. This is our xy, not function, our xy partial derivative. Now we have to plug in our values. Yikes. Let's make these smaller so we have more space. Let's plug in our values. So our double x partial, our double y partial, and our xy partial plugged in with value 0, 0. If you plug in 0, let's do this one first because it's easier. If you plug in 0 into our xy, we get negative 4 times 0 over 1 squared, which is just 1 still. So this is just equal to 0. And if we solve for our x partial, we get, so any case we have the x plus y squared, in parentheses, this just equal to 0 if we use 0.00. Equal to 1, sorry. It just equals to 1. So since we have a 1 here, 1 times 2 is 1 times 2 minus 0, because our x value is 0, minus 0 times anything multiplied by 0 is just 0, so this is just 1 times 2, which is just 2. So our entire numerator is 2. And this again is just 1 squared. So we get 2. And you can just plug that in yourself. I'm just doing some mental math right now. I'm explaining like the quick processes that I'm using rather than just plugging everything in. So again, this is just equal to 1, and this is just equal to 2. If we subtract 2y, and y is just 0, because we're plugging in for 0 here. Is equal to 0. This entire side just equals to 0. Therefore, this entire numerator is equal to 2. And this entire denominator is equal to 1. So it's 2 over 1, which is just 2. So far, xy partial is 0, and our xx and our yy partials are 2 and 2. What do? Well, all we have to do is just plug it into our second derivative test. 2 times 2, our xx partials and our yy partials, minus our xy partial squared. What is this equal to? Well, this is very, very clearly just a positive number. So with this positive number, what do? Well, again, our conditions, if dx or dxy is greater than 0, then this is a local max or min. What do we have to look at next? Well, since our d is positive, we just have to look at our double x partials. So our double x partial, what is it? Our double x partial is positive. Or is positive, if whatever notation makes you happier. So what is this? This will be a local min. Because the d is positive and our double x partial is also positive. Therefore, this point 0, 0, let's erase everything. Therefore, this point 0, 0 is local min. So, if you have any questions, put it down in the comment section. And just a quick recap, just to quickly warn you a little bit about these problems. The hardest part is quite literally just finding the critical points. Once you find the critical points to do all algebra, second derivative test, as long as you memorize that formula, it literally is like an instruction guide of telling you what to do, besides the conditions. So, hope you learned something.